Okay, so we are going to continue talking about infinite series. Um, so let me just remind us of some crucial facts. So an infinite series, remember, is just so we start with a sequence, right? A list of numbers. A series just adds them up. Okay. So we use our summation notation. And then the way we reconcile adding up an infinite number of things is through partial sums, right? So we defined this thing, the nth partial sum, where you're adding up the first n terms, and that those partial sums, right, become a sequence of their own. So the first partial sum is the first term, the second partial sum is the second term, the third partial sum is the third term, and so on. And so we take the limit of that sequence of partial sums, and if that limit exists, we take that to be the sum of our series. Okay, so that's our big idea for series so far. So what we're going to do now is we're going to look at a particular series. We are going to look at the geometric series. So let's start by defining what we mean by the geometric series. So a geometric series will look like a plus a times r plus a times r squared plus a times r cubed, and on and on and on. In our summation notation, one way to write this is the sum from n equals 1 to infinity of a times r to the n minus 1, right? In the first term, right, a is just a constant, and then this constant is being multiplied by what we call the common ratio r, by increasing powers of r, right? So in the first term, it's r to the 0. That's why we have this n minus 1. When n is 1, the power is 0. In the second term, the power on r is 1, so we get the n minus 1. An alternative way we could write this, just to play with indexing a little bit here, is instead I could index it starting at 0 and write a times r to the n, okay? Right? This will give you exactly the same series. Okay, either way is fine. The book writes it this way. I'm going to write it this way for now, so that if you want to, I'm going to do a computation that they do in the Stewart book, so you can follow it. I'll use the same notation for this, but we'll end up using both as we go along. So hopefully, as we get more comfortable with the indexing and all that stuff, that won't be much of an issue. Okay, so let's take a look at this sequence in a little more detail. I want to try to come up with a sum for this sequence, or decide if it even should have one. So remember what we do. We look at the nth partial sums, right? The nth partial sum will be a plus ar squared, and on and on and on, up to ar to the n minus 1. I'm using this indexing. So when n is 1, the power on r is, or is when the power on the nth partial sum, the power on r is 1 less than n, right? So I'm using this formulation. It won't change the result of this, but that's what I'm doing. Okay, this thing on the right is a pretty tricky thing to take a limit of. If you increase n, you increase the number of terms, right? And we don't really have a rule for what's happening if terms are increasing as your sum is increasing. So we're going to play a little game here. I'm going to take this thing and multiply both sides by r. I'm going to distribute it on the right. Okay, so I've multiplied it by r here, I've multiplied it by r here, and distributed it. So what happens is each a gets an extra power of r. A becomes AR becomes AR squared becomes AR cubed, and AR to the n minus 1 becomes AR to the n. Okay. Now I'm going to take this second equation and subtract it from the first. On the left-hand side, I get this. Something nice happens over here. Well, I've got A. Remember, this is just a regular finite sum up to some number. We can do things in any order. So when I'm subtracting all these from this, notice I'll get a negative AR and a positive AR. Those two will cancel. These two will cancel. There's an A cubed sitting in that dot, dot, dot. There's also an AR to the n minus 1 sitting in this, right? The one right before this. So every term is going to cancel except for this first A and this last one, which is being subtracted, AR to the n. Okay. Let's do algebra on both sides. I'm going to factor out S sub n and an A on this side, and then I'm going to divide by 1 minus R. 1 minus R. Okay. All right. So we've now got a nice compact expression. This S sub n is equal to exactly this S sub n up here. If you had numbers for all of these, and we'll do some examples eventually, you could put the numbers in here, put A and R in here, and go up to n, and you'll find that it'll add up to exactly the same thing. This is a nice formula for the nth partial sum. But what we really care about is, what is the limit of these partial sums, of the sequence of partial sums? So I'm going to take the limit as n goes to infinity on both sides. So when I take this limit, A and 1 minus R are numbers. Okay? And they're just constants. They're not changing as n changes. So they're a constant that I can slide out front. Now, what happens in here? Okay. Well, I asked you to take a look. There's an easy part. The limit of 1, the constant 1, doesn't change as n goes to infinity. In the previous section, the book goes through it in detail. We looked at, I gave this to you in the worksheet to do. What happens what is the limit as n goes to infinity of R to the n? And what you discover is the limit of this sequence is going to be 0 as long as R is between -1 and 1. Otherwise, the series is going to diverge, right? It's not convergent. So what does that mean? Well, if R is between -1 and 1, this is a 0, and the limit of this is just 1, and we get A to the 1 minus R. Otherwise, the whole thing diverges. So I'll just put if the absolute value of R is less than 1. That's just a simple way of saying between -1 and 1. Okay? So the limit as n goes to infinity of S sub n is this A over 1 minus R if R is the absolute value of R is less than 1. All right, so let's sum up what we've just discovered, or maybe proven. The geometric series, the sum from n equals 1 to infinity of AR to the n minus 1, which is equal to A plus AR plus AR squared, is convergent if the absolute value of R is less than 1 and its sum is n equals 1 to infinity, A to the R n minus 1. Its sum is equal to A over 1 minus R. Right, for R less than 1, absolute value less than 1. If the absolute value of R is greater than or equal to 1, so further away, outside of -1 and 1, the series diverges. Okay? So that is our geometric series, right? And this is pretty nice. There are a lot of series that we're going to see that are going to turn out to be geometric series, and we have a nice simple formula for computing them or knowing that they're going to diverge. So for instance, let's take a quick look at this sequence, this series. Well, let's start with the sequence 1 over 2 to the n. Right? We've seen this one already. This is going to look like, this is the sequence 1/2, 1/4, 1/8, 1/16. Right? Let's look at the series. N equals 1 to infinity of 1 over 2 to the n. This is, of course, 1/2 plus 1/4 plus 1/8 plus 1/16. Just want to rewrite this a little bit to put it in the right form. Let's not say the right form. Let's say in the familiar form as the series is written up here. So I can rewrite this as 1/2 plus 1/2 times 1/2 plus 1/2 times 1/2 squared plus 1/2 times 1/2 cubed, and on and on and on. We recognize this as the geometric series where A is 1/2 and R is also 1/2. Right? So this is a funny way to write this series, but these are exactly the same thing. And since R is between -1 and 1, we know immediately what the sum of this is. It's the constant term A divided by 1 minus the ratio 1/2, which gives me 1/2 over 1/2, or 1. Right? And we had looked at this earlier and decided that this seemed like the right sum for this series. So now we've seen it in a different context, how we can get to that sum. Okay. Let's do one more. Well, we're going to do a couple more. We're going to do two more things in this one. So let's look at another series. So let's look at the following series: 5 minus 5/4 plus 5/16 minus 5 over 64, and on and on and on. Let's see if we can figure out a way to sum this series. So I'm going to rewrite this. I'm going to notice a couple of things. I notice this 5 in each of them, so I might want to write this as 5 plus 5 times -1/4 plus 5 times 1/16 plus 5 times -1/64, and on and on and on. And maybe now I might notice I can rewrite this a little bit differently. Right? So -1/4 gives me this -4 in the bottom. 1/4 squared becomes 1/16. -1/4 cubed becomes -1/64. And so what we see is that this is just the geometric series where the constant term is 5 and the ratio is -1/4. -1/4 happens to be between -1 and 1. So we have our formula is 5 times 1 minus, we've got to be careful, 1 minus the ratio. The common ratio R is not 1/4, it's -1/4. So we get 5 over 5/4, or 4. Okay? And so we can quickly get a sum for that series. Okay? My instinct is to keep saying any questions. Of course, videotaping this. So I guess you're all doing great. All right, let's do one more thing. Let's let's consider this sequence. N equals 0 to infinity of x to the n. Right? So this is going to be x to the 0 or 1 plus x to the 1 plus x to the 2 plus x cubed, and on and on and on. Okay. Notice this again is a geometric series. It's a geometric series where the constant is 1 and the ratio is equal to x, which means this converges if the absolute value of x is less than 1. In other words, plugging in these values for a and r into my formula, remember the formula for our geometric series, we get a over 1 minus r. In this case, it's 1 over 1 minus x for x between -1 and 1. Right? Look what we have here. On the right, this is a function. And we've now represented this function as a geometric series. At least we've represented it for part of its domain, right? We're not representing it. The domain of this function is everything but 1. We've represented it only for a small portion of the real line. But it's still pretty interesting that somehow this infinite series, adding up all these powers of x, 1 plus x squared plus x cubed, and on and on and on, is equal to this function over this domain. Okay? Let's take a look. Let me do a little more to convince you of that, I hope. So let's just take a look at, I think we're sharing this now. So what I'm looking at here is a graph of the function 1 over 1 minus x. Okay, and notice our domain, here's -1 down here and 1 over here. So we're just looking at this place where I said this infinite series is equivalent to this. So I can't have the computer compute an infinite series, but what it can do is compute partial sums, right? So let's watch what happens. I'm going to turn this on. Right now, I'm only doing the first term. This is the function y equals 1. Right? I'm going to start adding terms. Here's 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed plus x fourth, right? I keep adding more and more terms. And look what we're getting. We're getting, we're getting at least over this domain of -1 to 1, we're getting a graph that's becoming closer and closer to this function, right? Of course, it still doesn't match perfectly. We can see it bending away as we get close to -1 here, right? This is because 50 terms is not very close to an infinite number of terms, but it also demonstrates, sorry about that. Oh, there we go. Right? You can see as I'm adding terms, give the computer a second to check up, notice what happens on the left and the right. This series is getting closer and closer to that function. Okay? So if you remember what I said at the beginning of the chapter, this is where we're headed. We're going to use these series to represent functions, and here's a great example of that. This geometric series, n equals 0 to infinity of x to the n, is equivalent to the function 1 over 1 minus x on this domain between -1 and 1, right? Where this blue one seems to be matching up with the red one. Okay, that is it for this one. See you next time.